For decades, a silent revolution has been humming in the background of our modern world. It is a technology born from the smallest building blocks of the universe, capable of providing near-limitless energy or devastating destruction. Today, we explore the intricate world of nuclear engineering, from the heart of the power plant to the frontiers of deep space. We often take the flick of a light switch for granted, but the journey of that electron likely began in a high-pressure environment where atoms are torn apart. This is the story of how we harnessed the binding energy of the cosmos to power our homes, our ships, and our future. The journey began in the early 20th century. Pioneers like Ernest Rutherford and Marie Curie peeled back the layers of the atom. But it wasn't until 1938 that Otto Hahn and Fritz Strassmann discovered nuclear fission. They found that hitting a heavy nucleus with a neutron could cause it to split, releasing a staggering amount of energy. The historical trajectory of this technology was accelerated by the pressures of the Second World War. The Manhattan Project proved that nuclear energy could be unleashed with terrifying efficiency. However, the post-war era shifted focus toward atoms for peace, aiming to transition this immense power from a weapon of war into a cornerstone of civilian infrastructure. At its core, a nuclear reactor is a sophisticated heat exchanger. Inside the reactor vessel, we find fuel rods typically loaded with uranium-235. When a stray neutron strikes a U-235 atom, it becomes unstable and splits into smaller fragments, releasing more neutrons and a significant amount of kinetic energy, which manifests as heat. To maintain a steady state, what engineers call criticality, we use control rods made of materials like boron or cadmium. These rods act as neutron sponges. By raising or lowering them into the reactor core, engineers can precisely manage the rate of the chain reaction, ensuring the heat output remains constant and safe. This heat is transferred to a coolant, often pressurized water or gas. In a typical pressurized water reactor, this primary loop transfers its thermal energy to a secondary loop of water via a heat exchanger. This creates high-pressure steam, which is then channeled to drive massive turbines connected to electrical generators. The engineering challenge begins long before the fuel reaches the reactor. Natural uranium consists mostly of U-238, which is not easily fissionable. To make it viable for power generation, it must undergo enrichment, a process of increasing the concentration of the U-235 isotope, usually via high-speed gas centrifuges. This is where the engineering of energy meets the complexity of international security. For a standard nuclear power plant, uranium is enriched to about 3% to 5%. However, the same technology used to reach these levels can, if pushed further, produce highly enriched uranium at 90% or more, the grade required for a nuclear explosive device. This dual-use nature of enrichment technology is the primary reason nuclear engineering is one of the most strictly regulated fields in existence. The leap from powering a city to creating a weapon is not a change in technology, but a change in the degree of enrichment, making the monitoring of centrifuge facilities a critical global priority. Nuclear energy isn't just for stationary power. Its incredible energy density makes it ideal for propulsion where refueling is impossible. In the maritime world, nuclear-powered icebreakers and submarines can operate for 20 years without ever stopping for fuel, using compact modular reactors to turn propellers and sustain life support systems. Looking toward the stars, engineers are revisiting nuclear thermal propulsion, or NTP. In an NTP system, a nuclear reactor heats a propellant, like liquid hydrogen, to extreme temperatures. The expanding gas is then exhausted through a nozzle to create thrust. This method is twice as efficient as the chemical rockets we use today. For even deeper space exploration, nuclear electric propulsion uses a reactor to generate electricity, which then powers ion thrusters. While the thrust is lower, the efficiency is unparalleled, potentially cutting months off a journey to Mars and allowing probes to operate in the dim light of the outer solar system where solar panels fail. Modern nuclear engineering is defined by defense in depth. This means layers of redundant safety systems designed to prevent the release of radiation. From the ceramic pellets that hold the fuel to the massive steel-reinforced concrete containment buildings, the goal is to ensure that even in the event of a total system failure, the environment remains protected. The challenge of back-end engineering remains the management of spent fuel. While often called waste, much of this material can be recycled in advanced, fast reactors. For the remaining high-level waste, engineers are developing deep geological repositories, monumental construction projects designed to keep material isolated for tens of thousands of years. We must consider the extraction of raw materials, the efficiency of the operational phase, and the ultimate decommissioning of the site. It is a multi-generational engineering commitment that requires precision at every stage. This is known as a life cycle assessment challenge. We must also acknowledge the moments when the complexity of the nucleus outpaced our control. The history of this nuclear power is marked by two names that changed our approach to safety forever: Chernobyl and Fukushima. These weren't just mechanical failures. They were reminders that the consequences of a breach are environmental, global, and multi-generational. In 1986, the Chernobyl disaster revealed how a combination of flawed reactor design and unauthorized operator testing could lead to a catastrophic power surge. It forced the global community to move beyond simple mechanics and define a safety culture where no single human error can bypass a critical shutdown. Fast forward to 2011, and the Fukushima accident highlighted a different vulnerability: the Beyond Design Basis event. While the reactors survived the initial earthquake, the subsequent tsunami disabled the cooling systems, proving that engineers must account for the most extreme natural worst-case scenarios imaginable. In response, the focus of modern nuclear engineering has shifted toward passive safety. Unlike older generations that relied on pumps and electricity, which can fail during a blackout, next-generation designs, like small modular reactors, use the laws of physics, such as natural convection and gravity, to cool themselves automatically. Mastering the atom requires more than just mastering physics. It requires a humble acknowledgement of its power. By treating every past failure as a blueprint for future resilience, we ensure that the nucleus remains a resource we can trust to power our future. The future of nuclear energy is moving toward two extremes: the very small and the very large. Small modular reactors, or SMRs, are being designed to be built in factories and shipped to sites. These plug-and-play reactors could provide carbon-free heat and power for industrial hubs or remote communities, with passive safety features that require no human intervention to shut down. Nuclear fusion. Instead of splitting heavy atoms, fusion involves forcing light atoms, like isotopes of hydrogen, together. This is the process that powers the sun. The engineering hurdles are immense, containing plasma at millions of degrees using powerful magnetic fields, but the reward is a virtually inexhaustible supply of energy with no long-lived waste. As we move toward a net-zero future, the role of the nuclear engineer has never been more vital. By understanding the history, mastering the complex physics of the present, and innovating for the future, we continue to refine our most potent tool for sustaining modern civilization.